We went through short dipole, went through arbitrarily long dipole, then we went through half-wave dipole. I'm going to start with the half-wave dipole one more time, talk about the gain formula or directivity/gain formula for it. I'm going to put down the electric fields, and I'll assume you know how to get the magnetic fields. From there, we're going to do the small loop antenna. You're going to see that the small loop antenna and the short dipole have identical gains. The difference is the radiation resistance for a short dipole, as given by Whitmer's book. It's actually off by a factor of 2, but is 40 pi squared L over lambda squared. Now, I'm just saying this. For a loop antenna, it's going to be in a complicated formula. When I say a loop antenna, it's a small loop where the perimeter is much less than a tenth of a wavelength. But almost always, small loop antennas are stacked. They make a helix. They're never just one. This is the thing you've probably seen if you see coil antennas. Questions now that we've got a full complement.
On a small loop antenna, is it still like, I'm assuming it's like a loop like this, and then there's still like whatever waveguide that would be in the middle, and that's where it propagates from?
Well, we'll talk about the directional propagation in the far field, but before I do that, I want to start with half-wave dipole. You all with me? And I got to show you some tricks. So I want you to be attentive because there's a quiz Monday. When you have a half-wave dipole, now this is and put this down, exact. It means it's exactly a half-wave. We're going to perturb this in a second. You'll see why. When you have an exact half-wave dipole, where the length of this dipole is a wavelength over 2, that's the free space wavelengths. We're assuming this is an air. It would be foolish not to do it in air. And you talk about the electric fields. This is the angle theta. We'll assume this is the origin. This is the distance r. The electric field in the theta direction is given by J60I. And that value of I is the value of the feed current here. It's not an average value. It'll be a peak value there for an exact half-wave dipole. Do you all follow me? We can get to the current distribution. 60I over, and this is over just R. There's not a 4 pi here. Then it's times e to the minus j beta r. Beta is 2 pi over lambda. After that, there's a function, and I'm going to call this small f of theta. Dr. Whitmer's book does not do that, but I'm doing it for a reason. And it's in the a theta direction. And the units are volts per meter. You had this last time. You all with me? Now, from that, if we're in the far field, and this is far field, by the way. The far field is when you're at a distance r greater than lambda over 2 pi. Do you all remember that? Now, that's only for a straight wire antenna. For aperture antennas, it's different, but don't worry about that. Just remember, for a straight wire antenna, the length of the antenna in wavelengths, or the length of the wavelength of the electromagnetic field you're propagating determine the far field, all right? So the longer the wavelength or the lower the frequency, the further away you have to go. For an aperture antenna, it's the opposite. An aperture would be something like a horn antenna that has an area, you might say, where the radiation occurs out of. This is for a straight wire antenna. If you have an aperture antenna, and I'll give you an example. Horn or dish antenna. All right. Then it's equal to 2, and it's d squared over lambda.
We're talking about far field?
Far field, but it's for an aperture antenna. And Whitworth will have this early in the antenna section.
428.
Do you see it? Does he have diameter d squared over
Yes,
lambda?
L.
Huh?
L.
L is, but it should be, what it is d is really not the diameter necessarily, it's the longest dimension. I want to mention something about this. So if this is a horn antenna, and this is A, and the height is B, this like suppose you have a waveguide feed into a horn. Remember the horn antennas I showed you guys? I think I showed them, right? What you would take is this dimension, it's the long dimension. So D here is equal to the square root of A squared plus B squared. Do y'all follow me? If it's a dish antenna, it's always the actual extreme diameter. And this determines how far away. But the thing you'll notice, so you have to be R greater than this. For this one, look, wavelength is proportional to what? Inversely proportional to frequency, right? So if I just put C over F for this, you can see as F goes up, you got to get further and further away from an aperture antenna before you're in the far field. This is counterintuitive. Here, lambda is C over F. As F goes up, you can be closer and closer and closer. So it is not something that necessarily makes complete sense at first. Go ahead.
So, but if F goes up, isn't D going down?
D is a measurement in meters.
Wouldn't
D doesn't
your
go
horn
down.
antenna- Well, wouldn't your horn antenna?
No, listen,
Maybe
constant,
the horn
you
antenna's
can radiate, if you have a dish antenna, it doesn't matter how high a frequency, the only thing the frequency to do is focus it more. And this is beyond us right now, but the thing is, the higher the frequency, when you have an aperture antenna, the further away you have to be for the far field. The reason that's important is when you're doing antenna measurements, you know where the anechoic chamber is on the fourth floor? How many do? Do you know what the anechoic chamber is? Do you know? Do you know?
Yes.
Do you know? If you don't, remind me afterwards, please somebody remind me. I'll take you up there and just show you. It's a bunch of pyramidal horns that absorb electromagnetic energy. It's about the size from this wall to that wall, maybe a little, about that far. Well, the field that it's radiated from the antennas they have in there has to be it has to be in the far field to get any kind of reflection and transmission coefficients that are meaningful. But if you go at too high a frequency for an aperture, then this is near field, and all your measurements go to pot. This is the thing you have to be aware of. In the real world, if you're working in they call it it's really a field measurements lab, and you do this kind of stuff, and a lot of people are just technicians. Doesn't always make sense to them, and they forget that. Straight wire antennas are different. So just remember that, all right? At least somewhere in the back of the mind, if you're in an anechoic chamber, figure out if you're in the far field and default to that kind of a measurement, because it's almost always aperture antennas. Anyway, this is the electric field from here. We talked about that. The actual directivity, D max, now this is for a exact half-wave dot, 1.64. Now, I'm putting that down there. See that F of theta? This is the field pattern for the electric field. The F of theta that goes in there, now some of you remember this. This is the exact half-wave dipole. This is going to be cosine of pi over 2 cosine of theta over the sine of theta. And that's the field pattern that goes right there. Can you all follow me? Now, I did this for a reason. When you look at the power pattern, we're going to square that. Right? We're going to get rid of the imaginary part too. So that's the directivity max, and I'll talk about that in a second. So the actual power density, average power density, is in the far field, 1/2 the magnitude of the E field squared over eta naught in the AR direction. You're going to see something about this on the quiz Monday. I'm going to find one way or other to get people's attention. Y'all hear me on that? And that is equal to, I don't know how many remember this. It was what? Something like 15, right? Over pi, right? Times what? I naught squared times what? The magnitude of F of theta squared. So it's that squared. Can you tell me where that formula is, Kenan?
8.8.
So R squared.
Over R squared, pardon me, over R squared. Thank you very much. And that would be watts per meter squared. Now, this is in the AR direction, by the way. 8.1?
3.81.
All right. So it's equation 8.81. Now, the normalized electric field for that, P normalized, is equal to simply that's, and I'll just put this, F of theta magnitude squared. So that's the reason I broke out f of theta. In Dr. Whitworth's book, he's going to use a capital F of theta, and he's just going to say that's my f of theta squared. Now the reason I'm doing this is because the electric field is proportional, or the power density is proportional to the square of the electric field, but both of them have that as the core, you might say, element of the actual pattern. All right, that's the reason. With me? All right, so I want to tell you about one other thing. When you look at P normalized, or by the way, what would the directivity then be for this, the actual directivity? As a function of theta, it would be d max, right, 1.64. And if you wanted to put the whole 9 yards in, you would put cosine of pi over 2 cosine of theta divided by the sine of theta, and the whole thing is squared. Now the directivity does not go to infinity, and I want to tell you this. See how that sine theta is in the bottom? Well, if theta is 0, the sine of 0 is 0, right? But at the same time, the top is going to 0 at the same rate. So when you do L'Hopital's rule on that, you'll find that this has a maximum value. This is the f of theta squared, or capital F of theta, right? It has a peak value of 1. It never goes beyond 1. Do y'all follow me? So if you plotted D max, and I'm going to show you. So if you looked at the power pattern, say this is the normalized, P normalized of theta. This is called the power pattern. For this, it would look like this. Matter of fact, let's do it instead of P normalized, let's just call it D of theta for the half-wave dipole. The peak value out here would be 1.64. Can y'all follow me? If this is a z-axis right here, and the peak would occur at 90 degrees, or broadside to the antenna. And I might add one thing. Anytime you're talking about radiation that is in the perpendicular direction from either an array of antennas or a single straight wire antenna, the direction is called broadside. Do you know where that comes from, that term? Anybody? That's right. In the old days, back in the days with sails and even with battleships, when they came and they put their guns to bear, the ship would turn so lengthwise it would be in the direction of fire, and all the cannons could be in this. It's called a broadside. That's where this term comes from. So the length of the antenna is this way. That's the broadside direction. And it's the same thing if that was the length of the array. Now, if you plotted on top of this the short dipole, that's the half-wave dipole. Go with me? The short dipole would look like this. If this is 1.5. Is there a waste can back there? There used to be a waste can here.
Is there not one in the front?
Not today. Can somebody just see if it's outside?
Yeah, it's by that.
Mind grabbing that thing? Anyway, if this is the actual half-wave dipole and you plot the short dipole, here it would be 1.5, and the pattern would look something like this. And yeah, thank you very much. You can leave it right there. Just right. The pattern would be almost the same, almost. Y'all with me? Very, very close. It'd be a slightly wider half-wave beam width, and there's a smaller peak value. So this right here would be the short dipole. And the black one would be the half-wave dipole. It's interesting to contrast this. Very close in either sense, right? Agree with that? Okay. Now, for an exact half-wave dipole, there's one other thing. This is important to know, the peak value. This power pattern, and by the way, I'll give you the power pattern, or the electric field pattern, and you should know how to get the power pattern. Tell you what, I'd give you this equation too, if you needed it. With me? But the thing about this is that you have to understand. The big difference is what I'm about to show you. When you look at the actual radiation resistance, and this is going to be for a lambda over 2 dipole, radiation resistance for an exact half-wave dipole is about 73.2 ohms. Now he has that in the book. It's roughly 72 to 73, but I got to be real careful about this because some of you guys are going to do antenna engineering. The whole thing with the actual impedance, the radiation resistance of an antenna, has to do with the radius of the wire that you're driving. When you get very, very thin antennas, you get a problem with losses. R loss goes up. All right, you're basically got a resistor in there because the copper will heat up. It doesn't have enough area, cross-sectional areas, to lower the resistance. And as you make the radius larger and larger, this starts going down, as I understand, to about 72 ohms. So just realize this is an approximation that's accepted. It's for a very thin wire, and we're not driving a lot of current. As you drive more and more, the wire gets fatter, and this will go down. Now, this is all for half-wave dipole here. The actual antenna impedance, so if you were to take a look at what you would replace the antenna with in terms of lumped elements so that you could calculate the current if you had a voltage. The antenna is about 73.2 ohms plus J42.5 ohms. But I want to tell you that 42.5 can change too with the thickness of the wire. Not a whole lot, but enough to at least you should be aware of it. It can change. And if you really want exact values, you've got to have a ratio. You really need to know the circumference of the wire and the wavelength that you're using, and there's formulas for this that you can look up. But there's tricks to this stuff. And in my EMC class, we go through all these things you need to consider for design. And when you're actually troubleshooting something, when there's a problem, you got to look carefully at the radiating part of it. You have to look at what antenna is actually radiating, not what they say. And there's some problems that happen.
You find that by measuring it, like do it in the anechoic chamber?
You don't need to measure this. Well, you could, but to be frank about it, the easiest way to do this, they have tons of tables on half-wave dipoles, and nobody uses an exact half-wave dipole. I'm going to show you something to get rid of that reaction, or reactive repeats. Now, this changes with length. If you start with a half-wave dipole and you start cutting it down, we're going to see we can get rid of that. It'll go to about 72 ohms plus J0. You keep cutting it down, and it'll go about 70 ohms minus J something. So there's a sweet spot where you get rid of the reactance as you keep cutting it down. That's what I'm about to show you. But all the formulas here are not appreciably changed. That's the nice thing. So this is an exact half-wave dipole. That's the impedance. To contrast this with the short dipole, I'm going to put right under there. For a short dipole, what is just the radiation resistance? This isn't even the total impedance. Do you remember? I mentioned it a second ago. Anybody?
80 pi squared, L over lambda squared.
Actually, he's right. It's 80 pi squared for the actual one that assumes the current constant. For the one that has a triangular current I talked about, then it would be 40, but he's right. It's 80 pi squared L over lambda squared, where L is length of antenna. And he doesn't even show the reaction, the reactive component of that in terms of length. And frankly, it gets a little complicated. By the way, this one is actually, for the really short dipole, it's not a plus J, it's a minus J. It's a capacitive term. Anyway, this was what it would be for a short dipole. And this is small. This is very small. Short dipole has to be a tenth of a wavelength or less, right? Just think about it. If L is a tenth of a wavelength divided by a wavelength, we have 1 over 10, right? Square 1 over 100. 80 by 100 is 8, or is 0.8. 0.8 times pi squared, it's less than 10, right? Less than 10 ohms. That's horrible. I mean, your copper losses now may be effective. It may take a lot of that power instead of radiating. By the way, you have to drive a lot of current to get any appreciable power out of it. Now, so what do we do with this half-wave dipole to make it something of use? We cut it down And here's what happens. Please write this down. His book, he mentions it. He doesn't go into detail. I think it's very important. So now, if we want the half-wave dipole to be an efficient radiator, and this is what everybody uses, all these electric field terms, the Dmax, the average power density, the electric field there will all be the same for what I'm about to show you. But then if we cut this thing down and we make a half-wave dipole, the length, instead of a half-wave dipole, we make it 0 point, and he should have, I think it's 0.485 lambda long. Kenny, can you check this out? Just, or anybody. Because this is the length that you take yours is 0.5 lambda, right? When you make it 0.485, can you tell me what that is?
I remember all
But I'm looking for the place. Is it an equation or just mentioning?
What is this?
That's the length of of a dipole where you get 0 reactive component. This is no JX component.
Page 460.
This is on page 460. Is it in the paragraph?
Yeah.
Okay. So if you make it that, this is a trick, by the way. Here's the length. If you make the length 0.485, and that's approximately true. It varies depending, as far as I know, depending on the radius of the wire. And one of the tricks you can probably do is, you know, if you take, have you ever seen these twin lead antennas that they have like a, if you just take a wire antenna, just take 2 pieces of wire, and then take a yardstick, or a meter stick, and then pull them out here so you have half a meter this way, half a meter this way. All right. Take that, let the wavelength there, or let the length, 1 meter be half a wavelength. Wavelength itself is 2 meters, right? From 2 meters, you can figure out the frequency. You all agree? Now, if you get that and you drive that at exactly a half wave, and you measure the current through that, going into that antenna, you get an impedance of 73.2 roughly, plus J42.5 for the actual impedance that you would measure for the current driving. And if you take some fingernail clippers, and I actually haven't done this, and you start snipping off a little bit of the ends of that wire, you have to tack it down, have some way of, all of a sudden you see that reactive component go to 0 when it gets down to about 485 lambda. And that's one of the neat things you can actually do and see it happening. And then you'd have no reactive components, so everything's radiated, or maybe some resistive losses, but that's it, there's no reaction. So if you get that,
You just have to plug into like a network analyzer
well, to measure the current,
or to measure the power.
do you know what a current meter is, a power meter? Have you ever seen the Rogowski coils? You just wrap it around stuff. Anybody here know what I'm talking about? All right, well, you know how time varying fields cause current, right?
Yeah.
If you take coils of wire, and we'll talk about this, and just wrap it around, a whole bunch of coils around an actual wire like this, well, the current's going in and out. The H field is going this way. There's a time varying H field for each loop. It induces a voltage. We know the frequency. From that voltage, we can figure out the current. And this is how power meters work. Like the Alabama Power, they never cut a line, but they can measure the actual current through it by finding the actual return current place or the feed current, and they wrap these little coils of wire around. They're called Rogowski coils. Anyway, if you take a look at this, if you're in the far field, all the field components, E theta and everything like that is identical to gain, everything to a half-wave dipole. The only thing is, the actual impedance, and this is the thing you write down, the Z antenna is about 72 ohms. Now, he'll have, I think, 73 ohms. Does he have that, or 72? But I think he has 72, but I don't remember. You see it in there?
73.
He has 73. This is one of those things, different books have different things. All right, 73. It's about 72, really, 70. And it's varying depending on the radius of the wire, but this is something useful, because when you get a half-wave dipole in the real world that's going to be used, that's what they're really doing. They're making it not exactly a half-wave, but 0.485 lambda, to get rid of that reactive component, because the reactive component limits the current, and that's the last thing you want if you're trying to radiate power. Follow me? Everything else is the same. Okay. Now, next thing I'm going to do is talk about the small loop antenna, one loop. And Whitworth does do it in terms of a differential magnetic vector potential A. He gets the dA from a small part of it. And then he says, well, this integration is beyond the scope of the text to get the thermoelectric field. So why you even do it? But at least you should understand that normally in all antenna work, what we do is we write down an equation for the magnetic vector potential, differential magnetic vector potential from a differential piece of current on that antenna. And then we integrate around the actual length or aperture of the antenna to get the total magnetic vector potential. Then we take the curl of that to get the actual H field. Once we have the H field, take the curl of that to get the E field. But that's the way it's really done when you take antennas and stuff like this. In Dr. Whitworth's book, he says the integral to get the total vector magnetic potential for that small loop is very difficult. And he's right. I believe it's an elliptic integral. And it's one of these pain in the butt integrals that I don't think he wants to do. And it isn't really necessary because you're not going to have to do it. But here's what I mean by a small loop antenna. If this is Z, and this is X, and this is Y, what they'll do is have some small loop here, and the loop will have some radius A. It'll be in the XY plane. And they assume they have a current I. And I is not going to vary anywhere in that loop. It's going to be the same everywhere. Now, the assumption is this, that the perimeter 2 pi a, that's the circumference of the perimeter of that, is less than lambda over 10. That's usually, he'll just have small, I think. Y'all see that? That's exactly the same thing as a short dipole. Take a short dipole and wrap it around, you got a loop. So you can mess with this, but I always say 2 pi a is lambda over 10. You can write it in terms of the area. The area is pi a squared, right? You could solve for a here. A itself would be, this is where the threshold is if you look at this. A is simply lambda over 20 pi. You can square that, multiply by pi. Now you have the area, and you could say area less than or equal to that. That's fine. A lot of different ways to define this. You all with me?
You said that's for far field?
No, that's the definition of a small loop. Far field will always be for this one, same as the straight wire antenna. It'll be lambda over 2 pi. Always the same for these small antennas. So for this one, you're going to come out here, and here is the actual way it's done. Because if you look at this, the current is swirling in the XY plane, and I want to make this clear. Whenever you have a wire antenna, a straight wire antenna, if there's a current I, and you come out a distance r away, and you look at this angle, this is real important what I'm about to show you. Current's in the plane of the board in the z-axis, right? The electric field will have to be in the plane of the board. You see how that thing's in the plane of the board? There will be no component of the electric field perpendicular to the board. No H phi, only an H theta. No E phi, only an E theta. Always, it's in the plane of the board. With a loop antenna, try to understand this. If you have a loop antenna with a current I, now the loop's in the plane of the board. Let's see. Call this X and Y. If R is in the plane of the board, so I'm making sure R is in that XY plane, the electric field will be in this direction. It will be in a direction, the current circulating this way, the projection of the electric field has to be something that is in the plane that the current's circulating in. This is real important. Now the H field will be perpendicular to it. But this isn't the far field. The E field will always be in that plane. So if you look at this loop, what does it mean out here? it means the electric field itself would be in the phi direction. Can you all follow me on that? It wouldn't be in the theta direction, it'd be in phi. It would be in the it'd be parallel to the xy plane and circulating this way. Do y'all follow me?
Is that because it's just the opposite direction of the current?
It's in the same direction the projection is.
Right.
See the xy plane, if you take this and project it into the xy plane, the entire electric field falls in the xy plane. There is no perpendicular component of that. It's a little hard to see sometimes. Can you see, imagine it? Just thinking, if R was in the xy plane, you feel out of the board, right? Move that up here. It'll always be out of the board. It'll be in the phi direction. Y'all with me? That is going to have no theta component. Theta would be this way, or this way. With me, class? I should say, yeah. Sorry, sometimes this would be E phi there. Way I've shown. Okay. So what are the field components? Here's what they normally do. Then I'll tell you why we don't do it, because the integration is a mess. If this is R, what he's going to say is if I have a differential current IDL here, it's going to give rise at R prime to some differential magnetic vector potential. It has to be in that direction. You don't have to write this down, but I'm just going to say I'm going to have dA here, and that's going to be equal to mu 0 over 4 pi. And it's going to be I dl, so it's probably going to be d phi times rho d phi, or a d phi, because we'll assume it's radius a d phi, it's in the a phi direction. It's divided by r prime. Well, r prime and r are about the same. And then you're going to get that e to the minus j beta. And here you're going to have r, I'm not even going to mess with this, I'll just call it r prime. As such, and it is in the a phi direction. Yeah, and it's hard for me to draw this. When you take that and you try to do this integral and assume that r prime, you write the equation for r prime, it becomes something called an elliptic integral. Has anybody heard of elliptic integrals? Have you heard of Bessel integrals or Bessel functions? Elliptic integrals, all these are special functions. Did anybody have an advanced mathematics course? Advanced engineering mathematics course? I recommend you take one. It will benefit you tremendously, especially when you get into higher level courses and stuff. Bessel functions, all these special functions really come about because they allow integrations of very complicated surfaces and things like that. That's the reason. Anyway, that integral he ain't even going to bother solving. What he's going to do is write down the final equation for A, and then he's going to take the curl of it. Y'all with me? After he takes the curl of that, he's going to take another curl of that to get the E field. Basically, two curls. And at the end of the day, he's going to find the electric field. And this is in his book. This is for the short dipole. Now, there's a lot of different forms for this one, for the short dipole. You'll have E, and it'll be in the phi direction, because he's assuming that the short dipole is in the xy plane. It'll be proportional to the current. The way he does it, I don't remember if he had, I'll just show you what it's going to be a function of. Let me write this down. He's going to have a function 1 over r. It'll have e to the minus j beta r here. It's going to be a sine theta here. It'll be in the a phi direction. And the units of this are going to be volts per meter. This is the electric field. Now, it'll be proportional to the current I naught, but what comes out here has a lot to do with who wrote it. You know how omega mu naught is the same thing as eta beta? All right, there's a lot of ways. There's so many ways to fashion this. In his book, what is he using for E? Oh, he uses, so this is really eta beta. So he has eta beta I, well, I'll tell you what, I'll put it, omega mu I S B over 4 pi r. So he leaves the 4 pi. He has 4 pi, he has omega mu naught, and then he has beta, right, in here, and he has s squared, or s, doesn't he? Yes, yeah. Just s, correct? All right, that formula I don't like, but that's okay. Beta is 2 pi over lambda. If you replace beta with 2 pi over lambda, you get 2 pi over 4 pi. So you get lambda over 2 there. It's a little easier. I would give you this formula, by the way. Now, S is the surface area, so S is really pi a squared. But the thing about this is that I want you to note, this has the exact same directivity and electric field pattern in terms of its shape as a short dipole. Remember, a short dipole is proportional sine theta? Short dipole is perpendicular upwards. Here's the way the equivalent, basically the equivalent of this. For a short dipole, you would have it like this, and you would have the same form of the electric field. This is, again, for the loop right here. But for the dipole, for short dipole, the electric field in the phi direction here is J, I'm going to try to show you the similar, J eta beta over 4 pi r. It's times L times I naught times e to the minus j beta r times the sine of theta in the a theta direction, volts per meter. Now, I'm doing this for a reason, so you can try to see the similarities and differences. If you look at this one for a second, I'm going to try to get your attention and do this in a way that this is something that's important to at least appreciate. You see how you have eta beta, right? Well, look, eta times beta, well, eta is equal to square root of mu over epsilon, mu naught over epsilon naught for free space. Beta is what? Well, beta is omega times square root of mu epsilon, right? I'm just making sure you see the reasoning behind what I'm showing you. All right, go ahead and do the math on that one. That means eta times beta. I have square root of mu, that's mu. Square root of epsilon's cancel, so I have omega mu. You all see how I can replace this by omega mu. You're going to see this. Got omega mu there, right? Just watch. Here I have a relative weight of the strength of that current and length. It's the product of L times I naught. You all see that? Here, my product of that is this. S times I naught. It's an area instead of a length. But it's a product. Now the beta here, there's no beta in this one, but there's a beta, the 4 pi obviously is there. The difference is that beta is there. And the beta is there for a reason. It's because it's a surface area in this one, and the beta is 2 pi over lambda. When you look at this, the units work then. I'm just showing you some of the things that I see. Same exact shape. The difference is obviously this is in the phi direction if it's in the xy plane. This is in the theta direction if it's in the z-axis or perpendicular to the xy plane. The gain is the same for this one. For a short dipole, I'm sorry. This is a small loop. I put short dipole. God, this is short dipole. This is a small loop. Keep me straight if I make mistakes. A little sleep deprived. All right, sorry, that was for the small loop, but you all see that, right? All right, now, that's the electric field. How would you get by the way, that's the electric field. How do you get the power density if you needed it? Anyone? Far field power density.
1/2 E naught squared over,
That's right. Y'all with me? That's what I always do. Now these forms, this stuff right here, all those coefficients, so many different ways to write this, and you look in different books, they'll have all sorts of different ways. They're a little more compact a lot of times, especially in EMC. They try to get the easiest possible formula. Now coming over here, the big difference here, and this is for the small loop, is this. The radiation resistance. And write this down for one turn, too. So if we have multiple turns, we multiply by n. Y'all with me, class? Because each time you have a turn, you're adding a series antenna, you might say. you're adding another small loop. You with me, class? So if you have this right here, the radiation resistance for this is going to be interesting. And I got to see the way he writes it, because to be frank about it, I don't remember the way he writes in his book. Radiation resistance, okay. So he puts the 320 pi to the fourth S over lambda squared squared. Now you don't have to remember that. So I don't remember that one. I'll show you something. Now, this is for a single term. I'm going to show you something. So this would be 320 pi to the fourth. I'm not sure where that actually came from. This formula I'm not real familiar with from my other work with EMC and stuff. S is equal to pi a squared over lambda squared. Keep watching. 320 pi to the fourth. Now I'm going to have pi to the fourth again coming out of there. And then I'm going to have a over lambda to the fourth. Y'all with me? Just watch this. S is pi a squared. That's the surface area. With me? Now, if that's pi squared times pi, sorry, this should be pi, I put pi, this should be pi squared, this should be pi to the sixth, just put it this way. 320 pi to the fourth times pi squared is 320 pi to the sixth. You all with me on this? Now I can just put a over lambda to the fourth power. And a lot of times, the way they actually do it, they'll leave a 2 pi in here, so it's the perimeter divided by lambda, and they'll square it, and you'll pull in a 2 pi. But that's an acceptable form too. This is in ohms. You can use this one, just make sure you know that S is pi a squared. I'm just warning you, sometimes people will make mistakes in this one. But one thing you can see, if you just think about this for a second. Suppose A, now that is a radius. Just do this for kicks. Let's see, 2 pi A, less than a tenth. Well, we can overkill. So let's make A just 1/10 lambda. With me? Watch this. If this is 1/10 lambda, then this is 1 over 10 to the fourth power. That's 1 over 10,000, right? 320 divided by 10,000 is 0.032, right? Times pi to the sixth, which I don't know, that's like 3 to 6. You're going to find out it's about the same impedance as a short dipole of similar length. As a matter of fact, I haven't done this one, but if you look at the impedance of if you put the perimeter of an actual loop antenna equal to lambda over 10, and you compare that to the impedance of a short dipole, I think you're going to see they're almost on top of each other, but I haven't done that one in a while. You all with me? So it's it's very low is what I'm getting at. Very low. Ridiculously low. What do you think the gain is or the directivity? Say directivity. We'll assume the efficiency is 100%. I think you know it. But, well, the fields are the same, right, in terms of their shape, the electric field. Doesn't that tell you that the normalized power pattern will be the same? If the E field has the same sine theta variation, if you square that, it'll be sine squared for power, right? Normalized power pattern is the same. What actually happens out of this is the directivity, D max for this one is the same as a short dipole. It's simply 1.5. And the total directivity as a function of theta is 1.5 times the sine squared of theta. Now that's really nice. With me? All right, so that's short dipole, arbitrarily long dipole, the field pattern we got. Then a half-wave dipole, exact half-wave, then a half-wave cut down to be equal to lambda, or 0.485 lambda, right? Got the field pattern, got the directivity, it's got all the stuff, radiation resistance, got everything of interest, right? Now what we're going to do is something for a monopole antenna. Then we're going to do Friis. Now, what's a monopole? here's where I have to do a little something with charge imaging. And this is a real useful technique. How many had me for EMAG 1 in here? Okay, then you'll remember this. This is a really useful technique. In my opinion. I know I'm doing a lot of theory in this one, I'm not applying it yet. But the theory right here is kind of important. Have an appreciation for this stuff before you just brute force problems. I think for random, it's more important to apply the theory. But for this one, you gotta see certain things. All right, so now we're talking about monopole antennas. What that means is we have to talk about current imaging and charge imaging. So I'm going to take a step back before we do this. Monopoles, instead of having 2 links of antenna center fed, you only have 1 link for a monopole. That's mono is 1. Di is 2, dipole therefore. So if we have a perfect conducting ground plane as such, and this is called charge imaging. And we have a charge here of plus Q at a height h. And I want to find the electric field out here, a distance r away. I want to figure out what E is here. Well, that's not a trivial problem. Whenever you have this kind of a situation, if this is a conducting ground plane, frankly, it's grounded, and that's V equals 0, right? So you can't get the electric field here by just saying, well, it's Q over 4 pi epsilon naught divided by R. Doesn't work. The ground plane will have an influence on that. Technically, the way you would want to solve this, if this wasn't a straight, if suppose it was some arbitrary surface, you would have to solve what's called the Laplace's equation in the dimensionality of the problem, either 2 or 3 dimensions. Del squared V is equal to 0 everywhere except where that charge is, and there it's a delta function. And then you would also, when you solve that, to get the E field, you would have to say E is equal to minus the gradient of the potential. Do you remember that from EMAG 1? The electric field is minus the, so that's, V is a scalar, but to solve that, that's second derivative of V with respect to x squared plus second derivative of V with respect to y squared plus second derivative of V with respect to z squared equals 0. Actually, it's equal to a delta function that occurs at this point. I'm not going to do this, but I'm just telling you what you would have to do if you wanted to do it right. And the delta function would have like delta x times delta y, and then it would be times delta of z minus the height, and then there has to be a singularity function there that's going to be, there'll be a 4 pi involved, but I'm not going to get into this. This is beyond the scope of this class. But when you solve this thing, you have to match that boundary condition. And that's an infinite series solution, I'm just going to tell you. But a way you can get the solution very easily is say, and it mathematically works, is say if we want the electric field here, we can get a charge image. We can just say, let's eliminate this ground plane entirely and put an image charge directly below there at a height h of the plane, but don't make it a charge plus Q, make it minus Q. Do you remember that from EMAG 1? This is the handiest little tool. So to get the total electric field here, I would say this, the electric field total would be the electric field from this charge, the electric reason I'm not at the NBA. It would be the electric field from this charge, Q plus, and then it would be plus the electric field from the negative charge that's imaged. Y'all with me? And this would be, call this R1, and this would be R2. Can you all follow me in this class? I'm going to remember that. Charge imaging. If you take a look at what happens to currents, and then this won't be hard to see. let's do the same thing, but now we're going to consider currents, but in terms of their actual displaced charges. If you have a current parallel of length L, running parallel at height h to this ground plane, are you with me? It's got a finite length. What actually happens with current, we're talking about for electrical engineers, is this positive charge moving. It's creating a plus charge here and displacing a minus charge here. This is the way it's explained typically. You all with me? Now, that means this is imaging down here a positive charge, and right below here at a distance h, and if this is at a height h, right below here at a distance h away, there's going to be a minus charge right here, right? Now you can do this, there's a little bit less charge here, 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 here. You can go through the mental gymnastics about this, but what is actually happening here is there's a current imaged here in that direction. Can you all follow me? So currents parallel to the ground plane, a conducting ground plane, image in opposite directions. And if you wanted the total radiated electric field, if you're in the far field from that, you could say it's the total radiated field from this one, E1, and then you would have to also add to it the total radiated field from that one, E2. And that would be the total radiated field at some point R in the far field. Y'all with me? So what if you have a current that's vertically oriented? Suppose I have a current like this. Assume that a height h, call it h1, and here it's h2. Don't worry about the length. Y'all with me? All right, here's a plus charge, here's where the plus charge is. So if I come down here at a distance h1, h2, I would have a negative charge. Do you agree with that? And then here, come down a distance, and now that was a minus q, this would be a plus q, and it looks like what? Now that current image is in the same direction. Y'all with me? This is called the method of images. Therefore, currents that are perpendicular to a conducting ground plane image, there's the images in the same direction. If they're parallel, they're in opposite directions. And in EMC, this is real important. Electromagnetic compatibility and radar and probably some designs. It's very important to understand that. So when we talk about a monopole antenna, here's what we do. If we have a dipole antenna like this, we assume the same image or the same signature of current is above or below that ground plane. And this is the length of the antenna, right? I mean, that's the way a dipole is, and we know if we have a dipole antenna, we know how to get the electric field out here, right? We can do it for a short dipole first, but you all follow my reasoning on this one? Take a moment, make sure you see what I'm talking about. So, what if I do this? Let's assume we have a short dipole for starters, all right? So I'm going to take a short dipole, so L is going to be less than lambda over 10. And that means if it is a short dipole, then this electric field, you don't have to write this down, just follow the train of thought, is J eta theta I naught L over 4 pi R e to the minus j beta R times the sine of theta in the a theta direction, volts per meter, right? This is important. Look over here for a short dipole, the radiation resistance is equal to 80 pi squared length over lambda squared ohms, right? Can you all follow me on this? The directivity also, D for a short dipole, will be equal to 1.5 sine squared of theta. And lo and behold, we have all the information we need basically to get anything we want. I could write down what the radiated power density is, but basically from this we can get it all. Do you agree with that? Everyone? Now, what happens if we take this and we get rid of that image and just put a ground plane there? So now I'm going to have this situation. Same short dipole, right? And this is a short dipole, so this length now, this wire, actually, let me do it this way. This length is going to be the length of that short dipole only by 2. So if it was 1/10 of a wavelength long over there, here it's 1/20 of a wavelength above this ground plane. And now when I drive it with my voltage source, and I feed it, it's going to have a current. Right? With me? And from that, and it's measured right from, remember there's an image, there'd be an image right here, have the same length, same current, remember this current's in this direction, same exact current, and we give rise, as a function of R and theta, to an identical electric field. E out here for the short monopole, this is a short monopole. Going to be the same exact thing. J, eta, beta, I naught, L. But now this L right here is going to be the actual dipole length. So it's got to be the length of the short dipole over there. Are you with me, class? In other words, if this length is L over 2, the L here is the thing you worry about. That L is the same thing as, L over 2 is the quarter wave, or is the short monopole here. It's over 4 pi r. It's times e to the minus j beta r. And it's going to have the same exact sign variation, a theta. Here's the difference. I'm going to, and it'll be in the same direction. I'm going to ask you something. Do you agree the power density radiated here will be the same as the power density radiated here? If the E fields are the same, it has to be the same. What's the real difference? Over here, the power density is radiated over spherical surface. It's everything, right? It's an entire spherical surface, right? Here, it's only radiated over the upper hemisphere. You see this, everyone. It doesn't radiate into the ground. Because it only radiates in the upper hemisphere, has the same current, with me? The radiation resistance of this one will be half the radiation resistance of that. Remember, power radiated, I'll put it down, P rad is equal to 1/2 I naught squared times R rad. If the same electric field exists as over there, right? But the power is only radiating in half of over a hemisphere, not a full sphere, this radiation resistance is half of the actual radiation resistance. So for a short monopole, R rad here will be equal to, now it will be 40 pi squared. But this is going to be the dipole length. This is the thing that you got to be careful. This is L of a dipole, not monopole, over lambda squared ohms. So it's exactly half of the impedance of a short dipole. Here's another thing that happens because of this. The directivity is doubled. Because the power radiated is only in the upper hemisphere, the actual directivity is doubled. So for a short monopole, the directivity, right here, and I'll just put that, D of the monopole is going to be 3, not 1.5, it'll be times sine squared of theta. Y'all with me? And that always works. I always try to explain it this way. Sometimes I do a better job than others. Now, if you think about this, let's extend this to the half. Remember, there's a half wave dipole. Now we're going to do a quarter wave monopole. Everybody with me? If we have a half, or let's do a quarter wave monopole. So we're going to have a lambda over 4 monopole, but I'm gonna draw from what I just did with a dipole. I mean, a short dipole. I bet you guys get this. So here's the ground plane. And the length of this is now lambda over 4. Remember, it's going to have an image current just like it would for a half-wave dipole. If you have a current I naught, and I'm assuming the current is I naught, right here, the driving point impedance of this will be 1/2 the driving point impedance of a half-wave dipole. With me? This is a quarter-wave monopole. So here, the Z antenna is going to be actually and this is for the monopole. This is lambda over 4 monopole. Now this is normally 73.2, but if you divide that by 2, I think he's going to have, I'll just put 73.2 by 2. That's what, 36.54, something like that. Y'all with me, class? You can just leave it. It's that plus J 42.5 by 2, which is 21.25, J 21. But you get the idea. It's half the impedance of a half-wave dipole. The electric fields out here at a given distance r away, the electric field and the power pattern are going to be the same as for a half-wave dipole, which will be J I naught, right, or 60, so J 60 times I naught over R times e to the minus j beta r. And then here you're going to have that cosine of pi over 2 cosine of theta over the sine of theta in the a theta direction, volts per meter. You'll get that. You're going to get the same power density only in the upper hemisphere. Remember, it can't radiate into below the ground plane, you might say. Nothing radiates below that. It's a perfect conducting plane. The power density out there will be the same. Now here's the deal. The radiation resistance, or the actual, that's Z antenna. So you can see the radiation resistance is half that. What is that? About, or 36.5, something like that. Anyway, you can figure out it's approximately that for the radiation resistance. But now the directivity, and this is for lambda over 4 monopole, is double that of the directivity for, so it's going to be 2 times 1.64, so it's 3.28, and then it's going to be times cosine of pi over 2, cosine of theta, sine of theta squared. And that's the whole thing with the monopole. Now if you cut that thing down, take 0.485 and divide it by 2, and you cut that thing down, then the radiation, you get rid of the imaginary parts, just about 73 divided by 2, which is 36.5 ohms. With me, class? And it would be for a half-wave monopole. Now, almost all of these antennas that you see that are straight wire antennas above the earth, matter of fact, I can't think of any that aren't. Now, some just have loop antennas up and down, but any straight wire antenna, like the old AM radio, AM radio basically is low frequency. They'll have a long wire straight up. They get an image in the ground, and it will be a half-wave, let me cut down, about a half-wave dipole trim, so you get that. Almost always. There are exceptions, and I can't pretend to know all the exceptions. Long ago, I got a second-class license in FCC to be a radio telephone or engineer. I could be like a radio station engineer. I could do stuff like that. And I remember there are all these FCC laws that govern a lot of stuff that you're allowed to do, transmission power, length of antenna, wire, gauges, and all that crap. But the real truth is, you just got a monopole for all that, for AM transmission, a lot of transmission. Shortwave antennas just use a straight wire antenna. You know what the Morse code is? Dot, dash, dot, dot. All right, well, long ago when they had civil defense and when they had any kind of emergency management and crisis management, they would have shortwave radios as the only kind of communication they could get. And it would go all around the world. with shortwave radio, they can have a 10-meter band. Most people would use 10-meter bands. This was real popular. Think about it. Before the internet, you had one way to communicate if you wanted to talk. It was a telephone company, which was expensive. You want to talk to your friends in Australia or China from here, if you want to spend a little more money and buy a ham radio, you could have no problem talking at night to them, and it wasn't a real problem to do that, honestly, if they had shortwave radio. It saved a fortune. And that was real popular before the internet. Now the internet's everywhere with Starlink, so even in the Amazon forest, people can communicate with tribes that make jewelry out of animals, and basically, and they can do commerce with them because of that. Well, that's a step in the right direction. But before that, ham radio, straight wires. I don't have time to get in the Freese. I'm going to Freese on Monday. The quiz will include some of the things I talked about today, but a lot of the stuff I talked about today is just leftovers from before. With me? So no, short dipole, half-wave dipole, cut short. And I'm going to put a few extra problems up there, and I'll see you Monday.